Welcome back to the deep dive. We are definitely shifting gears today. We spent a lot of time on high-level architecture lately, but today we are going deep into the trenches.
Way down.
We're looking at overflowing function pointers.md, and honestly, this is the kind of stuff that keeps security engineers up at night.
It really is. It's one of those vulnerabilities that sits right at the intersection of, slightly sloppy coding and really deep system architecture.
And we're not just talking about crashing a program today.
No, crashing is easy. Any amateur can segfault a program. That's just a denial of service.
Right, it's annoying, but it's not elegant. Today is about execution control. It's about hijacking the flow of a program so it runs code it was never, ever supposed to run.
And doing it right under the nose of the operating system. To really get this, though, you need to leverage everything we covered in the C Fundamentals notebooks. We're sort of assuming, your way around memory.
And we're going to apply it to a really specific case study, a program called gameofchance.c.
Which is a fantastic example of how a tiny feature, a single game setting, can open the door to a massive exploit.
Okay, so before we tear that code apart, let's just establish the core concept here. We're talking about function pointers.
Right.
Now, if you're working in Python or Java, this might feel a bit abstract. But in C, a function pointer is, well, it's just a variable, isn't it?
Is. In the C memory model, code and data. They're not that different. They both just live in memory at some address. A function is just a sequence of instructions sitting somewhere.
So when we declare a function pointer, we're basically creating a variable that holds the address of that function.
It's a map coordinate. Tells the computer, go here and do this.
Okay, so that's the vulnerability right there. What happens if someone changes that map coordinate?
That is the exploit. You use an overflow, you overwrite that pointer, and you make it point to completely different code.
So let's look at the target, gameofchance.c. The notes say this comes from a hacking book example. Walk us through it.
It's a simple multi-game program. You can play dice, play cards, that sort of thing. And it needs to track who's playing their score.
And crucially, what game they played last for the play again feature.
Exactly. And to keep all that info together, the developer bundled it into a struct.
A struct user.
Right. And you need to visualize this. A C struct is just a block of memory. The fields are packed in one after another.
So let's look at those fields. You've got, say, a character buffer for the user's name.
Let's say 100 bytes.
100 bytes. And then right after that, maybe an integer for the user ID, a score, and then this function pointer for the current game.
And that order is absolutely critical. If the name buffer comes before the function pointer in the struct, they will sit side by side in memory.
Which brings us to the flaw. The program asks for the user's name.
And it uses a function to read that input. Now, if the programmer was careful and used something like surrogates where you specify the length, we wouldn't be having this conversation.
But they didn't. They used something like Stracky. So I'm the attacker. I see a 100-byte buffer. I don't type Bob. I type 100 A's.
You fill the buffer.
And then I keep typing.
And the program doesn't stop you. Those extra bytes you type spill over into the adjacent memory. First, you might overwrite the OID, then the score.
And then, if I calculate the offset just right,
You overwrite the function pointer.
and this is the difference between just crashing the program and actually hacking it. A script kiddie just types 500 A's.
Right, and the pointer gets overwritten with garbage, like 0 by 41414141. The program tries to jump there. It's not a valid address.
Save fault. Game over.
But we want control. We don't want to write garbage. We want to write a very specific address. We want to point that instruction pointer somewhere useful.
So in this game, what's our target?
Well, in these kinds of challenges, there's usually a hidden function. Maybe a jackpot function that prints a secret flag or something.
And we can find the address of that function pretty easily, right? With standard tools.
Oh, yeah. You'd use something like mm. You run m, game of chance, it lists all the symbols, and you just find jackpot and copy its memory address.
Okay, so let's say the address is 0 by 0804845B. I can't just type that on my keyboard.
No, and this is a detail that trips up a lot of people. You have to deal with byte ordering. Most modern processors are a little Indian.
So you have to write the bytes in reverse order.
Exactly. Your payload would be 100 bytes of junk, then maybe some padding for the other variables, and then 5B by 4 by 04 by 08.
So when the program reads that into memory, it flips it back around, sees the correct address, and when it tries to play again,
It jumps to jackpot instead. You've hijacked the control flow.
But hang on, there's a huge detail in the notes we're kind of glossing over. This only works so reliably because of where that struct user is stored.
Yes,
The notes say the variable player is a global uninitialized variable.
that is the absolute key to this specific exploit.
Why? I mean, if it were a local variable in the stack, we could still overflow it, couldn't we?
You could, but stack exploits are more dynamic. The addresses on the stack can change every time you run the program. It's a moving target.
But global uninitialized variables,
Right.
they go somewhere else.
They go to the BSS segment.
BSS, block started by symbol.
That's the one. It's just a special fixed chunk of memory that the compiler sets aside for globals that don't have an initial value.
So because struct user player is declared at the top of the file outside of any function.
You go straight to the BSS.
Yeah.
And here's the kicker. In a standard executable, the BSS is at a fixed static address. It doesn't move.
I see. So every single time I run Game of Chance, that player struct is at the exact same memory address.
Correct. The distance between your buffer and the function pointer never, ever changes.
Yeah.
It makes the exploit perfectly predictable.
It effectively removes the chance from the game of chance.
It does. It just turns it into a math problem.
Now let's talk stakes, because the notes add this terrifying little detail about the lab setup. It says, note, user is password for current user running notebook with sudo privilege.
Right. And this is where we go from a cool trick to a critical vulnerability.
Sudo, super user do. It elevates your privileges to root.
So if you're running a program as a normal user and you hijack it, you can only do what that normal user can do. But if the program is being run by an admin with sudo,
Then the process itself has root privileges.
yes. And if that process is running as root and you hijack its instruction pointer,
The code you force it to run also runs as root,
so you redirect that function pointer to a call that spawns a shell.
and you get a root shell.
You own the box. Total control of the machine.
And this all started from a sloppy streepy into a global struct.
It really is a comedy of errors. The global variable puts it in the BSS, which gives you a static address. The struct puts the buffer and the pointer next to each other. And the missing bounds check builds the highway for the attacker to drive on.
It's interesting, the source material seems to be from a slightly older style of hacking. You know, smash the stack from the late 90s.
It is fundamental, though. Modern systems have protections like ASLR, which randomizes memory locations, and NX bits that prevent code execution in data segments.
So it's harder now.
It's harder, but the logic is the same. You can't understand modern techniques like return-oriented programming if you don't understand these fundamentals. You have to know how memory is laid out.
Let's go back to the game of chance code itself. I'm trying to get inside the programmer's head. Why use a function pointer in a struct like that?
It's about state. Imagine you finish playing the dice game. The program asks, play again. If you say yes, it needs to know what game to play again.
Right. Otherwise, it has to ask you again. Bad user experience.
Exactly. So the current game pointer is literally just a bookmark. We were just here.
Uh.
And since player is a global variable, that state is available to every function in the program.
It's convenient.
Globals are seductive for that reason, but by making it global, they put it in the BSS and gave the attacker a static map.
I want to circle back to the copy, examine, compile steps. When it says examine, what am I actually looking for in the source code?
You're looking at the definition of struct user. That's ground zero. You have to count the bytes. Char name 100 is 100 bytes. Then int is another 4.
So my offset isn't 100, it's 108 plus maybe some padding.
Exactly. You can't just guess. You often have to use a debugger like GDB, crash it with a recognizable pattern.
The cyclic pattern technique.
Precisely. You send a unique string, see what value lands in the instruction pointer, and that tells you the exact offset. Turns guesswork into science.
So if we pull back to the big picture,
Yeah.
we have the mechanism overflowing a buffer to overwrite a function pointer.
We have the location, the
Yeah.
BSS segment, for our global uninitialized variable.
And we have the impact. Full execution control, potentially at the root level.
That's the trifecta.
For the developers listening, the takeaway is pretty obvious. Don't use strict B.
Please, use Strike BP, check your bounds, and, just avoid globals if you can. It's not just about clean code. It's about reducing your attack surface.
And for the security researchers or just the curious minds out there?
The takeaway is, don't trust the code. The computer does what the memory tells it to do. If you can change the memory, you can change the reality of the program.
Data becomes control.
That is the fundamental axiom of binary exploitation. We are tricking the CPU into treating our data as its own instructions.
It's fascinating and terrifying.
It is. So we talked about how the BSS is predictable, but what about on a modern system with ASLR? Is this just unexploitable now?
That's a great question.
It's not unexploitable,
Yeah.
just harder.
Hmm.
ASLR randomizes things, but if the program wasn't compiled as a position-independent executable BIE binary, the BSS might still be at a static address.
So legacy code running on a modern OS could still be a sitting duck.
Absolutely. Compatibility often trumps security. You can't assume the OS will save you from bad code. Security has to be in layers. Secure the code, the compiler flags, and the OS.
That's a critical point. A patch server doesn't mean your binary is safe.
Not at all.
Well, this has been a proper deep dive. We went from what is a pointer all the way to calculating offsets in the BSS. I have a new appreciation for the humble struct.
And hopefully a healthy fear of Stracopy.
Always. Thanks for breaking this down. It's complex, but understanding the bits and bytes is the only way to really get how these systems break.
My pleasure. It's always fun to look under the hood.
And a final thought, building on something from the notes. We saw how gameofchance.c used a pointer just to remember the last game played, a harmless little convenience feature.
Right.
So think about this. If something that simple creates a backdoor because of where its variables are stored, how many other convenience features in the software you use every day are sitting in the BSS segment just waiting to be overwritten?
Something to think about.
Good advice. Thanks for listening, everyone. We'll catch you on the next deep dive. Stay safe and keep your buffers checked.